Let's jump into 20.2, calculating change in entropy for a reaction. So just defining terms first, standard entropy of a reaction, which is given the symbol delta S naught. Delta S naught, let me kind of zoom in here. Delta S naught of reaction, that little degree sign right here just means that all reactants and products are at standard state. That means that it's at 298 K, a pressure of 1 atmosphere, etc. So if you need more explanation on that, please refer to your book. But let's go on to predicting the sign of change in entropy. So remember, entropy is a measurement essentially of disorder in a system, or a measure really of freedom. It's kind of easier to think of it as disorder because it relates more closely to everyday scenarios. But entropy is specifically the measure of freedom in a particular scenario. So let's look at the example of cyclopropane being heated and converted into propene. So this is cyclopropane. Got a little cyclic organic molecule here. And then when it is heated, we signify that or symbolize that by drawing a little triangle for heat, and then that is converted into propene. All right, so going from one state to another. I'm not even going to actually signify the states of matter, but looking at these two molecules, in order to answer what the delta S of the reaction is, we have to really compare what the freedom of motion of the products is and compare that to the freedom of motion of the reactants. So if let's say the freedom of motion of the products was larger than the freedom of motion of the reactants, then the answer would be that this is greater than 0, that delta S is greater than 0. Okay, with that in mind, how would we compare that? So we compare that by looking at the types of bonds that are involved on the right-hand side and the right-hand side and the left-hand side for this particular reaction. If we were looking at a reaction that changed states like solid to gas or a liquid to gas, that's typically much easier. But if the states of the matter stay the same, or maybe they're not even indicated and they're assumed that they stay the same, what we're really looking at is the bonds involved. So this carbon to this carbon, there's a double bond right here. So this is restricted in motion. This can't actually rotate around this bond. It is restricted motion, but this carbon and this carbon are singly bond, so that means there's free rotation here, that this carbon with its 3 hydrogens can freely rotate. Now let's compare that to this molecule right here. This molecule is actually restrained in movement because each one of these is involved in 2 bonds, right? Two bonds of carbon bonds. So this carbon is bonded to 2 carbons, this carbon is bonded to 2 carbons, etc. So really all of the motion here between the carbon bonds is restricted, whereas there's one that's restricted here, but this carbon bond is not restricted. So we would say that the right-hand side has a higher entropy than the left-hand side. The left-hand side would have a lower entropy or lower freedom. So when you're comparing that, taking the products minus the reactants, the answer would be that the delta S of the reaction is in fact greater than 0 because there is more freedom on the product side than there is on the reactant side. Okay, so how do we actually calculate a delta S, standard delta S value from a reaction? We are going to use, in this first scenario, standard entropy values from Appendix B in your book. So in order to calculate delta S, it's a very similar process as calculating delta H in your previous chemistry class. We're also going to use a similar process when we calculate delta G, which is to come. That is just taking the sum of the moles of the products, entropies, and subtracting from that the sum of the moles of the reactant entropies. So we're going to put that into practice in this upcoming example question. So here we're going to calculate the standard change in entropy. That's what delta S of a reaction is. Standard change in entropy. So it's like this for the Haber-Bosch process. And the equation for the Haber-Bosch process is nitrogen plus hydrogen makes ammonia. So what you would see in the back of your book are these three entropy values in Appendix B. They are specific for the states of matter, so do be aware of that. And we're going to use this equation to solve for delta S of the reaction. So I would suggest pausing the video here. Go ahead and set that up, and then play the video when you are ready to see the solution. All right, so this is how your equation should look like when you input all of your values. So to calculate delta S of reaction, I have to take the standard entropy for the products, which is 193 times the 2 moles of the products, and subtract from that, and this is kind of a small subtraction, so I'll just make it a little bolder. Subtract from that the entropies of the reactant, so 191.5 is nitrogen, and there is 1 mole of nitrogen, and then for hydrogen, which is right here, 130.6 times 3 moles of that. So when you put that all together, then you will get negative 197.3 joules per Kelvin, just 3 sig figs, even based off of the subtraction, the fewest number of decimal places is in 193, so my final answer would be 197 joules per Kelvin. Great, let's go on to the next slide. All right, so let's start to get into the comprehension, the understanding these processes part of this lecture. So in example question 1, I ask, how can a process be spontaneous if delta S of the reaction is negative? And I tell you to see the second law of thermodynamics for assistance. So yet again, I want you to pause the video, give each other some ideas. What do you think we need to take into consideration here? Why am I bringing in the second law of thermodynamics? So a good place to start is just write down what the second law of thermodynamics is. From there, you'll see something that relates to this portion of the problem. Okay, so how will that tell you something about a spontaneous process? How does that tell you what is necessary to be true for a process to be spontaneous? So again, start with writing down the second law of thermodynamics, pause the video, discuss for 2 minutes, and then you can press play again. All right, so hopefully you got to discuss just a little bit, and you wrote down the second law of thermodynamics, which states that the change in entropy of the universe is equivalent to the change in entropy of the system plus the change in entropy of the surroundings. For any real spontaneous process, that has to be greater than 0. So what you should have pointed out is that delta S of the system is the same as delta S of the reaction. Yes, one is at standard state, the other isn't. It doesn't matter that it can or cannot be at standard state. But for a reaction to be spontaneous, you just need the sum of both the change in the system, which is usually the reaction that we're studying, and the change in the surroundings to be greater than 0. So let's say this number right here, this delta S of the system, which again is delta S of the reaction. This is just a more specific term for delta S of the system. Let's say this is a negative number. How is the sum of these two still greater than 0? Well, this just has to be a larger positive number. So that means the surroundings play a large part in determining whether or not a reaction is going to be a spontaneous process or not. So that's what we're going to explore now. Okay, so in order to analyze what's happening in the surroundings, we want to see what's happening with this transfer in heat energy. For an exothermic process, that means that heat is leaving the system. So that means our Q is less than 0. So if the heat is leaving the system, that means it's going to the surroundings. Think of the labs you did last semester or previously in which you took, a hot metal and put it into water. Well, the heat left the metal, which was the system, and went to the water, which were the surroundings. All right, so by virtue of the heat going to the surroundings, that means delta S of the surroundings is greater than 0 because the more heat energy, the more energy states are available for the molecules to occupy, which means your number of microstates increase, which means, again, you have a greater change, a positive change in entropy of the surroundings. The exact opposite is true for an endothermic process. So for an endothermic process, Q of the system is greater than 0 because the system is gaining the heat from the surroundings, which means Q of the surroundings is less than 0, which would mean delta S of the system is what is a positive number or greater than 0. Again, whatever gains more heat energy, that allows for more energy levels to be occupied by the molecules involved in that system, which then allows for an increased number of microstates. Higher number of microstates means a greater entropy. All right, but the temperature at which that happens, at which the heat is transferred, does have an effect on delta S of the surroundings. Delta S of the surroundings will be greater, so a greater change, when heat is added at a lower temperature. And the reason is because delta S of the surroundings is equal to the amount of heat that's transferred, negative the amount of heat that's transferred, over T. So when T right here is a lower number, this makes delta S a larger value. At constant pressure, that just changes Q to be delta H. Remember, heat at constant pressure, so QP is really equal to delta H. So that's why we make this equivalent to delta H when heat is at constant pressure. So then we get this delta S of the surroundings is equal negative delta H of the system over the temperature at which the heat was transferred. So let's do this upcoming problem. Calculate delta S of the universe. So we're really calculating both delta S of the surroundings and the system and putting them together for the synthesis of ammonia. So the previous problem at 298 K. Here are the steps we are going to employ. So first, we're going to write down the second law of thermodynamics. We're then going to plug in delta S of the reaction. We're then going to find delta H of the system at standard state. We're then going to solve for delta S of the surroundings. And then step 5, we're going to plug in delta S of the surroundings to solve for delta S of the universe. So what I want you to do is step 1, pause the video, do step 1, and then we'll do that until we finish through step 5. Okay, this is what you should have written down for step 1. Second law of thermodynamics, I didn't include is greater than 0 on here because we're going to be able to determine if it's greater than 0 or not and if it's a spontaneous reaction after we plug in the next values. So let's do step 2. Go ahead and pause the video again and let's do step 2. All right, so now if we plug in delta S of the reaction from the previous problem, which you should get is negative 197 joules per Kelvin for delta S of the reaction at standard state. So go ahead and pause here again. Let's see if we can solve for delta H of the system. You will need to use Appendix B in your book to do so. All right, for delta S of the system from the back of the book, you should have gotten negative 45.9 kilojoules per mole for our product, which is ammonia. There are 2 moles of that. And then for both nitrogen and hydrogen, the delta H values are 0. So your final answer for delta H of the system then would be negative 91.8 kilojoules per mole. Again, pause the video here if you need to write the rest of this down, and then it is your task to solve for number 4, delta S of the surroundings. To do so, remember you're going to be using this equation up here. All right, after solving for delta H of the system, then we need to solve for delta S of the surroundings. To do that, we're going to use this equation up top, all at standard state in this scenario. All right, so the only little correction I have is this is at delta H at standard state. When I plug that in, I'm plugging it in for 1 mole of the reaction. That's why I'm just going to plug in negative 91.8 kilojoules in here. I don't include the mole because it's 1 mole of the reaction already. The difference is I do plug in terms of joules or units of joules per Kelvin instead of kilojoules. And the reason I do that is just because my delta S of the system is in units of joules over Kelvin. So I just want to stay consistent in that. So I'm plugging negative 91.8 in terms of joules, dividing it by the temperature, which should give you 308 joules per Kelvin. So the last thing we're going to do is plug in delta S of the surroundings up into the equation at the very top to calculate for delta S of the universe. So pause the video, solve the problem, and then play again to check your answer. Therefore, your final answer on this problem should be 111 joules per Kelvin, which means yes, it is a spontaneous process because delta S of the universe is greater than 0. All right, let's go to our last problem on this page. All right, so it's a fill in the blank. For processes approaching equilibrium, the change, so now we're tying in the idea of equilibrium and entropy. It's going to get a lot more fascinating. For processes approaching equilibrium, the change in entropy of the universe is greater than 0. When at equilibrium, the change in entropy of the universe is what? It's 0. Because it is no longer spontaneous in either direction. If it is not spontaneous, if it will not go in either direction, that means the entropy of the universe is 0. So let's finish out with our last page. All right, solve for or calculate delta S of the universe for 1 mole exactly of water. Vapor condensation at equilibrium. So I do want you to attempt this, but first let's just talk about what it's looking for. So a reminder, delta S of the universe is equal to delta S of the system plus delta S of the surroundings. All right, vapor condensation at equilibrium, that means water. And I think specifically, yeah, we're going to go the vaporization phase. So we're going to go from a liquid to a gas. And this is going to be at 373 K because that's 100 degrees Celsius. That's when water spontaneously or is at equilibrium between the liquid and the gaseous phase. So that's when it's at equilibrium between the liquid and the gaseous phase. So the first thing that we're going to do is solve for delta S of the system at standard state. That means we're going to solve for 1 mole of the material. So specifically, we are solving for delta S at standard state and delta S of surroundings at standard state. This doesn't, in this scenario, mean it's at 298 K. It just means we're at 1 atmosphere with 1 mole of the material. So go ahead and look up those values for delta S or for the standard entropy values for water in Appendix B in your book and see if you match my values. And then let's solve for delta S. All right, so 195.9 joules per Kelvin is what I get for my product, which is the gas. And then 86.8 is what I get for the liquid in units of joules over Kelvin. If I subtract those two from each other, what you should get is 109.1 joules per Kelvin. Okay, so that is our delta S of the system. So we still need to solve for, let's do a different color, delta S of surroundings at standard state. We know that's going to be negative delta H of the system over temperature. So we do need to solve for delta H of the system. This one's a little different because we, since our delta S values don't take temperature into consideration, it's not a huge deal that we are at 373 K. However, the delta H values in the back of your book are specifically at 298 K. So since this reaction is happening at 373, I do have to give you the values for delta H of the system, and that is 40.7 times 10 to the 3 joules per mole. Now we can plug that into our delta S of the surroundings. So that means delta S of the surroundings is equal to negative 40.7 times 10 to the 3 joules, because we're just dealing with 1 mole of the reaction, divided by 373 K. Go ahead and pause, see what your answer is, and then check back with me. All right, so when I do that, divide my delta H by T, I do get negative 109 joules per Kelvin. So that is my delta S of the surroundings. So notice these two are equal opposite numbers. So that means my delta S of the universe, it's kind of hard to see, is equal to 0 joules per K. Because remember, when anything is at equilibrium, delta S of the universe is 0 because it is not spontaneous in either direction. So this was just a proof as to why delta S is 0 at equilibrium. Delta S of the surroundings and delta S of the system are equal. Let's go on to spontaneous exo and endo changes. So no matter the enthalpy, a reaction occurs just because delta S of the universe is greater than 0. So these are our two main scenarios we're dealing with. We're dealing with exothermic process where delta H of the system is less than 0 and delta H of the system is greater than 0. So exothermic and endothermic. This is exo, this is endo. Okay, so what's the reason, again, why a process would be spontaneous? If the heat is leaving the system in one case, and if the heat is going to the system in another case. So, for example, in a case where the reaction is exothermic and spontaneous, you might have something like the combustion of glucose. Turning into carbon dioxide and water. And in this scenario, heat is produced. So that's why it is an exothermic process. Let me just erase this, get this out of the way. Okay, so since heat is released, the surroundings have a greater energy. So delta S of the surroundings is greater than 0. delta N of the gas, just looking at how we would kind of predict what delta S of the system would be, delta S of the gas is greater than 0, though, so that means that delta S of the system is also greater than 0. So we're looking at scenario A. So if delta H of the system is less than 0, yeah, delta S of the surroundings is greater than 0, but delta S of the system can also be greater than 0. So if you have two delta S values, delta S of the system and delta S of the surroundings, that are both greater than 0, like scenario A, that means delta S of the surroundings is greater than 0. Let's say you had a scenario, though, this should say system. Let's say you had a scenario where delta S of the system was less than 0. Well, still in that same scenario, if the reaction is spontaneous, that just means that delta S of the surroundings is much greater than 0. Okay, so you can have a system, you can have a scenario where the process is still spontaneous regardless of what your delta S of the system is, if it's positive or it's negative. Basically, what I'm getting at is the other delta S, the delta S of the surroundings, just has to be a lot greater, a much greater positive to overwhelm a negative delta S of the system value. So again, really the major point that I want to focus you at here is that enthalpy is not the deciding factor in spontaneity. Delta S of the system is. So no matter if you have an exothermic or endothermic process, as long as the addition of the two delta S values gives you a positive for delta S of the universe, then the reaction is spontaneous. And that is it for today.